Yeah, so currently we're coding a BFS after going through the content in the slides. And in order to actually add this neighbor to the queue, we would just have to say queue.add neighbor. So this is our complete BFS over here. Are there any questions about how it works? We can run this and make sure there are no errors. And then we can also add print statements to understand what each thing is doing. Okay, so there's no errors. Underneath the line where we're getting the current vertex, let's print out visiting and then followed by current vertex to understand what it's doing. So when we do this, you can see it prints out visiting 1, visiting 2, visiting 3, visiting 4, visiting 5, visiting 6, visiting 7. And that's because it starts off at vertex 1, and then it adds 2 and 3 to the queue. Then it goes to 2, it goes to 3, it goes to 4, 5, 6, and 7 in that order. And let's actually go to our get adjacency list method and alter it a bit and test out something that was related to um, a question that was asked earlier. So instead of putting 1 and 2 first, let's put 1, 3, and then 1, 2. And now let's run our code. So now when we make this change, you can see immediately the order of the vertices changed. It prints out visiting 1, visiting 3, visiting 2, visiting 5, visiting 4, visiting 7, visiting 6. Whereas earlier it was 1, 2, 3, 4, 5, 6, 7. And the reason for this is because now if we print out our adjacency list, if we print out the vertices that vertex 1 is connected to, so you print out what vertex 1 is connected to, you can see it's 3 and 2. Because 3 is first in the list, when we're going through our for loop, 3 is the first neighbor. And that's why 3 is going to be added to the queue before 2. So I just wanted to demonstrate that to answer Neil's question from earlier, where he's asking why it went to B before C. So it really just depends on what order it is in the adjacency list. But the main thing to note is it's still visiting the vertices in order of distance. 2 and 3 are still 1 unit away. 4 and 5 are still 2 units away. And then 6 or 7 are still 3 units away. Are there any questions at all about this BFS? Hey, great. Let's move on to our DFS next. So a DFS. Remember, a DFS is a depth-first search. We're going to go as far as we can down one path, then come back up and repeat. In this example, we will do a DFS from vertex A. A DFS can use recursion or a stack. So remember, with BFS, we have to use a queue. With DFS, we can use a stack, which is a similar sort of data structure, but slightly different. Or we can code it using recursion. And I like to code it using recursion because it's only like 4 lines of code, which is really neat. Plus, we also learned recursion in APCSA, so this will be a good review. So DFS pseudocode. We start by marking, so we have a DFS function because we're going to be using recursion. And the DFS function takes in the vertex that we're going to visit. So inside of our function, when we're visiting a vertex, we set it equal to true, visited vertex equals true. Then we go through each of the neighbors that the vertex has, much like a BFS. We check if the neighbor is not visited, and then we call DFS on it. And that's all it is. So you can see this is pretty much the same thing as a BFS, except instead of using a queue, we're just using recursion. And that is going to be very different. It's actually a pretty big difference doing a BFS versus a DFS. Because remember, with the BFS, we could figure out, okay, B and C are each 1 unit away from vertex. 2 and 3 are each 1 unit away from vertex 1. And we could figure out 4 and 5 are 2 units away, and 6 and 7 are 3 units away. You cannot do that with a DFS, so that's important to note. If you ever wanted to figure out how far a vertex is from another vertex, you have to use a BFS. You cannot use a DFS. Okay, let's take a look at a more detailed demo. So the red circle represents which recursive call we're currently at. If you remember in APCSA, we had to create like a recursion trace table, something like that. This is what this represents over here on the left. So we're going to do our DFS from B. We do our DFS from B, and we look at what neighbors B has. B has A as its neighbors, C, and E. And it doesn't really matter which one we go to first. In this example, we'll just go with A. So A is its neighbor, so we're gonna call DFS A. We look at what neighbors A has. A has F as a neighbor, so we call DFS F. So now we visited A, we visited F, and from F, we look at what F is connected to that's not visited. Except the thing is, everything that's connected to F, which is just A, has already been visited. So that's why we're going to go back up our recursive call. So we're going to go back up to A, and then A has nothing else to it's connected to that hasn't been visited. So we go back up to B. We reach the end of the path. We go back up to A and look for other unvisited neighbors. We go to B. So now we're back at B. We visited this branch. So does everybody get that fundamental difference between BFS and DFS? Like DFS will explore a branch as far as it can. This kind of looks like a tree. This actually is a tree, by the way. Remember, trees have n vertices and n-1 edges. So we visited this branch fully, this branch of the tree. Whereas what a BFS would have done is it would have gone A, C, E, and then it would have gone F, G, D. That's how a BFS would have worked. But that's not what a DFS does. So now with from B, we go to C, which is its next neighbor. From C, we're going to go to D. From D, there's nothing else to go to. So we go back to C. From C, we go to G. Once again, there's nothing to go to from G, so we go back up to C. There's nothing to go to from C. This should be orange, by the way. I forgot to color it. So from C, we go back up to B. And now we visited this branch completely. So now we're at B, and there's only one vertex we haven't visited, which is E. So we go to E, and once again, there's nothing to go to from E. So we go back up to B, and we're done. We're done with our DFS because there's no more vertices to visit. So that's just the general way that a DFS works. Are there any questions about that? Any questions? Okay, great. We'll code a DFS. It's really short. So I'd already put the function get adjacency list in the chat. Go ahead and copy that and create like a new class for the DFS. So a new DFS class. Or if you want, you can comment out your code on repo, whatever you're using, whatever is convenient. But just make sure you have the get adjacency list function in your code somewhere in your class. And now inside of our main function, this is where we're going to make our recursive call to DFS. Before we do that, we have to actually build up our adjacency list. And I'm going to make my adjacency list global. Because I'm writing a function, I don't want to keep on passing in my adjacency list into the function. So I'm just going to have a global variable for my adjacency list. Still the exact same as before, just outside the main function. Inside the main function, I'm going to give it its values, adjlist equals get adjacency list. Remember, I gave you guys this function that fills it up for us, so we don't have to type it out. So just use that. And another thing that we need is we need the Boolean array to keep track of what we visited. That doesn't change. That's still the same from a BFS to a DFS. Because we don't want to keep on visiting the same thing over and over again. And the size of this Boolean array is the size of our adjacency list. So I'll pause here for a bit. Are there any questions about this part? Is everybody here? Okay, if everybody's here, that's good. We just have our adjacency list and have our visited array. Now we're going to write our DFS function. And remember, this DFS function takes in an integer. It takes in an integer. the vertex that we want to visit. So we're going to do a DFS for the same exact graph as we did for the BFS, which is this graph over here. Okay. No, actually, wait a second. Yeah, we'll do a DFS for this graph over here. And then we can make some modifications to it, that's fine. Okay, so we have DFS, and now we have to actually write the DFS function. So that's going to be static void DFS, and we're going to take in a vertex. Who remembers what the first step is when we visit a vertex? What's the first thing we have to do?
Add the neighbors? Or is it actually, do you set it to visited?
Yep,
You set visited to true?
Yep, we say visited vertex equals true. And then after that, we add the neighbors. And this is why DFS is so short, because we can just use a for each loop. We can say for each neighbor in adj.getVertex. For each of these neighbors, if the neighbor is not visited, so we use the not sign. If not visited neighbor, DFS neighbor. That's it. Doing a DFS is as simple as this. This is all the code that we need. We mark a vertex as visited when we go to it. We go through its neighbors. We check if it's not visited. If it's not visited, we do a DFS on it. And let's go ahead and print out which vertex we're at. So you can print out visiting and then vertex. And let's run this code. Visiting vertex 1, visiting vertex 3, 2, 4, 5, 7, 6. Let's take a look at that order. Because, is it this one? Yeah. So it says it goes to, it says it does 1, 3, 2, 1, 3, 2, 4, 5, 7, 6. So 1, 3, 2, 4, 5, 7, 6. Now, how in the world does that work? Let me draw on this. So it just went from here to here to here. No, actually, it went from 1 to 3. Never mind. It went from 1 to 3. Come on. Okay. It went from vertex 1 to 3 to 2 to 4 to 5 to 7. And then it magically leaped to 6. How did it do that? Well, if you remember, a DFS will try to go as far as it can down one path. And that's exactly what it did over here. It went from 1 to 3 to 2 to 4 to 5 to 6. It just kept, 5 to 7. It just kept going down this path. But from 7, there was nowhere else that it could go. So then what it did after going to 7 is it came back to the call for 5. There's nowhere else to go for 5. So it came back to the call for 4. And from 4, we could go to 6. 6 was unvisited. So that's why it went to 6. And that's just a demo of how the DFS does not go in order of distance from the starting point. It just goes as far as it can on one path, and then it comes back up. Let's just make a slight modification to our DFS function. So you could copy and paste this if you don't want the original function, if you still want to have the original function. I'm going to make a modification where we also, when we're doing a DFS, we also keep, just a second, I'm thinking about something. Yeah, I'm going to make a modification where we keep track of how many calls it has been, how many calls I've had, how far away from a, yeah, just let me think about this for a bit. Yeah, let's just print out the order that the vertices are going, that the DFS is going in. So we're passing this 0 as well. We've taken a second variable called, I guess we can call it depth. It's not quite depth, but, and then in our DFS call for on line 26, we'll say depth plus 1. And now what we'll do is when we're printing out that we're visiting a vertex, before we print that out, we'll iterate, we'll print out depth number of spaces. This will make sense in a bit. We'll just print out depth. We'll print out a space. Let's run this now. Yeah, and you can see, okay, yeah, it did do what I wanted it to. It prints out what exactly it's doing in the DFS. So you can see it's visiting 1, then it visits 3, it visits 2, it visits 4, it visits 5, it visits 7. That's the end of that path. So then it visits 6. And if you look at the indentation, you can see the indentation between 7 and 6 is different. The indentation for 5 and 6 is exactly the same, because from 4, it's going to go to 5 and 6. So this is just a useful slight modification we made to a DFS function if you wanted to see how it's visiting the vertices. And note that this isn't the shortest distance from the starting vertex. This depth variable over here, that's not what that is. You would have to use a BFS for that. So are there any questions about a DFS? Hopefully that little modification we made also helped clarify some doubts you may have had about the DFS algorithm. Questions? If there aren't questions, then we're going to go ahead and we're going to code we're going to practice more BFS and DFS because these are really important algorithms. And we're going to gain some more hands-on experience with them. Okay, so there's something called a bipartite graph. And a bipartite graph is basically a graph in which we color the graph's vertices with 2 colors, either one of 2 colors, red or blue. And the goal is to do this coloring in such a way that no 2 neighbor vertices, remember neighbor vertices are ones that are adjacent to each other, have the same color. So in this graph over here, it's actually in the shape of a it's actually in the shape of a hexagon. And we can see over here that this is a bipartite graph because if you look at adjacent vertices, they're all different colors. You don't have a red next to a red, you don't have a blue next to a blue. But if you look at the graph next to it, the pentagon, we have these 2 reds that are next to each other. So this graph is not bipartite. It's not possible to color it so that no 2 neighbor vertices have the same color. So how could we figure out, given a graph, given an adjacency list, whether or not it's bipartite? And if you took a guess, you could probably guess with pretty high confidence that the answer would be a BFS or a DFS, because that's what we've been learning about. And yeah, we could use both a BFS and a DFS for determining whether a graph is bipartite or not. In this example, when we're coding it, we're going to use a DFS. And I thought I had some slides on the logic for doing it, but oh yeah, I was going to explain it live. Okay. So let's take a look at how does everybody understand what this what a bipartite graph is and what we're trying to figure out?
I have a question. Can't uneven like for example a hexagon can be a bipartite graph, but the one on the right it would never be bipartite, right?
Yeah, a
Okay.
hexagon can be bipartite. Like if I colored all of these red, then that graph bipartite is that term just basically means is determining whether or not it's possible to color it in any way. so that that condition is met.
I
So in
see.
this case, it's possible to do it with this hexagon. With this pentagon, no matter what combination you try, it will never be possible for this condition to be met. Therefore, it's not bipartite.
Okay, so we're checking if it is possible to be
Yeah.
bipartite.
Yeah,
Okay.
checking if it's possible. Yeah. Yeah, so how could we do this with a DFS? Because that's what we're going to use to code the solution to this problem. Let's say we start our DFS at vertex 1 and we go to vertex 2. And just by, I'm going to choose red, green and red to be my colors for the vertices. So I start by coloring vertex 1 with green. So vertex 1 is green. I'm doing my DFS to vertex 2 now. And by the way, all the vertices in the graph start out uncolored. We're just going to use an interarray to keep track of the color of each vertex. It all starts out at 0 because they're uncolored, and then we'll give them colors. So we give vertex 1 the color of green, and now we DFS to vertex 2. Because we know for a fact vertex 2 has to be a different color from vertex 1, we'll color it with red. So we're at vertex 2, we'll do our DFS from vertex 2, we'll go to vertex 4. Because vertex 4 is connected to vertex 2, we know for a fact it has to be green. And we just continue doing this. For vertex 4, we go to vertex 6, that has to be red. Vertex 6 is not connected to anything else. So we look at what else 4 is connected to. 4 is connected to 5 over there. So 5 has to be red because 4 is green. And 5 is connected to 7. So 7 has to be red. I mean, has to be green because 5 is red. And remember, if you were to make like a recursion table or whatever the actual term for it is called, um, we would snake our way all the way back up to vertex 2 because we're done going as far as we can on this. Actually, we're not done. Sorry, my bad, my mistake. From vertex 5, we can go to vertex 3. I forgot about that. Um, so from vertex 5 is connected to vertex 7, which you just visited and labeled with green. Vertex 5 is connected to vertex 3, which has not been visited. So now we go to vertex 3, and because we're coming to vertex 3 from vertex 5, which is red, we color vertex 3 with green. Does anybody see a problem?
Yeah, 1 and 3 are both green.
Yeah. So far DFS thinks everything's good, there's no problem, until it gets to vertex 3, and it looks at vertex 3's neighbors, and because they're already visited, 1 and 2 are already visited, so it's not going to go to them again, but it's just going to check in on their colors and see what their colors are. And it's going to check in and see, wait a minute, 1 is already green, and I'm green as well. So that's an issue. That means the graph is not bipartite. This graph over here is not bipartite. And that's how we can determine whether the graph is bipartite or not. So in this example, we just saw that this graph over here is not bipartite. And I'm trying to come up with an example of how it could be bipartite. So let's take a look at a bipartite example. If I modified this graph by deleting these two vertices, these two edges, now I color this green, I color this red, I color this green, color this red, I color this red and this red, I color this green, and nowhere in my DFS when I'm checking the colors of neighboring vertices, so I'm at 3 and I'm checking 1 and 5, nowhere in this graph when I did my DFS would I have found an example where two adjacent vertices had the same color. That's how a DFS can be used for determining whether a graph is bipartite. Whether it's possible to color it in any way. There may be like a million ways to color a graph. We just want to know if there's even one possible way to color it to meet this condition. And a DFS can be used to solve this problem. And BFS can be used. We're not going to code a BFS because, as you saw, BFS and DFS follow the same exact logic, except it's a recursion versus a queue. So let's go ahead and code this now if there aren't any questions about that solution. So I'll create another class. I'll create another class and I'll call it bipartite checking. Once again, copy over that function that we had, get adjacency list. That way we don't have to type everything out. And in our main method, what's the first thing that we want to do? We're going to write a DFS function. So just as we did earlier, we're going to write an eventual DFS function that's going to handle this bipartite checking. But there are some things that we have to do first. I'm also going to copy this over from our DFS code. So we are going to need an adjacency list. We are going to need a visit array. That's always stays the same for the most part when you're doing a DFS or DFS. This code over here is also going to be the same. The code to get the adjacency list and get the visit array, that's going to be the same. I'll copy that over. And I did mention that one thing that we will be using to keep track of the colors is an int array. So I'll also create a static int array. I'll call it colors. And then inside of my main function, I'll say colors equals new int. The size of this array is the number of vertices we have. The number of vertices we have is the size of the adjacency list. And there I'm done creating my variables and initializing them. So let's go ahead and write our DFS function. And this DFS function is actually going to return a Boolean. It's not going to be void. It's going to tell us whether it's possible to color the graph in such a way that it's bipartite. So I'll say Boolean is bipartite. Boolean is bipartite equals to DFS1 and 1. I'll explain what these parameters are in a second, and we still have to write our DFS function, so don't worry if it's red. I'm just handling printing out the results. I just want to do that first before we actually dive into that the logic. So I'll print out the graph is, I'll just say the graph is, and I'm going to use something called a ternary operator. Basically what it does is it's like a shortcut for an if statement. You type in your condition, your Boolean condition, followed by a question mark. After the question mark, you type what you want to do if it's true. So if it is bipartite, then we want to print bipartite, or we want to have it a string bipartite. Then you type a colon followed by what you want to do if it's not true. If it's not true, we want to say not bipartite. I just thought I'd drop that in there as a little extra piece of information. And now, yeah, let's actually discuss our DFS function, what it's going to do. So just like before, it's going to receive the vertex that we want to DFS to. And it's also going to receive the color that we're going to use for the current vertex. In this case, we're going to use 1 to represent green. We'll use 1 to represent green. And 2 equals red. Okay, let's write our DFS function. It's going to be static Boolean DFS. It's going to take in a vertex as its first parameter, and the color is the second. And what's the first thing that we're going to do in our DFS? It's the same thing as last time. Does anybody know? Okay, the first thing that we're going to do in our DFS function is set the vertex as visited. We say visited vertex equals true. And because we also want to color this vertex, we'll say colors of vertex equals color. So now we've visited the vertex and we've colored it. Just like we would in a traditional DFS, we're going to go through each of the neighbors. So for int neighbor in adj.getVertex, and this is where the logic's going to be a little different. If we have visited a vertex, so if you visited a neighbor, then we want to, so I'll add a comment here, visited neighbor. If we visited a neighbor, then we want to check the neighbor's color. Because we want to make sure there's no conflicts with our color, so this color over here, and the neighbor's color. That's why I'll check over here. If the color, so if colors of neighbor is equal to colors of vertex, so vertex is where we're currently at, then this is bad. The colors are the same and they're adjacent matrices, adjacent vertices. So I'm going to return false. My DFS function is going to return false. Does everybody follow along with that? And if the neighbor has not been visited, then that's fine. That means we have to visit it now. So we have to give it a new color, basically. We'll start off by saying int new color equals 1. And then what we can do is we can check if color equals 1. So if our current vertex is 1, we're going to set new color equal to 2. And now that we have the new color and the neighbor vertex that we want to go to, we can say DFS neighbor and pass in this new color. We can take this result and store it. So we'll say Boolean result equals DFS blah, blah, blah. And then what we'll do is we'll check if the result is false. So remember, this DFS returns whether there are any discrepancies. So if there is a discrepancy because two neighbors have the same color, and if that result is false, then we also want to return false from our function. We don't care about the rest of the neighbors that the vertex has. We already know that it's not possible to color this with just two colors, so we return false. Now it's in red, this function is in red because the last thing we have to do is at the outside of our for loop, we have to return true. So if everything's fine and none of these conditions here are ever going to be false, then we return true from our function, and it is possible to color the graph, and it is bipartite. Are there any questions about this?
Can you stay on that page for a little bit? I'm still working on getting the code down.
Yeah. And you can just see over here printed out the graph is not bipartite.
Okay, thank you. I caught up.
Mm-hmm. The next thing that we're going to do is play around with this a bit more. We know that it works if the graph is not bipartite. In this example over here, all we had to do was delete these two edges, and it did become bipartite. So let's go ahead and delete the edge between 2 and 3 and 4 and 5 and make sure that that works. So open up the get adjacency list function, and then you can see here we have 2, 3 lined up with each other. This is an edge list, by the way. I'm making an adjacency list from an edge list. It's just convenient to do that instead of having to type adj.add, adj.add, adj.add over and over. Just create an edge list, loop through the edge list, and add the stuff. So we're going to delete the edge from 2 to 3, and we want to delete it from 4 to 5. So 4 and 5 line up, we want to delete those two numbers. Let's run this now, and it should print out the graph is bipartite. And there it is. It printed it out. The graph is bipartite. Yeah. So that's how you check if the graph is bipartite. Is everyone comfortable with how this works? Everything from using the visited array to what the DFS does to the adj.get vertex using the adjacency list. Is everything cool? Great. And if anybody else needs some more time to get the code down, you can let me know. If not, there's one more thing that we're going to do before our next break, which is determining the distance between edges in our graph. So you have our graph over here, and let's say we want to figure out how far vertex 1 is from vertex 4. Remember, I said we cannot use a DFS for this. We have to use a BFS. B is in bag. So let's go ahead and start coding this part now. So I'll create a new Java class. I'll call it BFS distance. And like I've done the past couple of times. Just gonna go ahead and copy that get adjacency list function. I'm gonna create a main function. What is one difference between a BFS and a queue? Pop quiz. You can tell me one difference between the two.
Between a queue and what?
Between a BFS and a DFS.
Oh, okay. DFS goes all the way down the line, and BFS searches for neighbors.
Yeah, that's correct. That's where we're going to use a BFS to calculate the distance between the two vertices. And the BFS uses the queue structure. So if you need to, you can also have the original BFS code that we had written open. I'm pretty lazy. I'm just going to copy a lot of it because it is the same for the most part. So we have our adjacency list, we have our queue, and we have our visited array. And now our goal is to do a BFS from one. And when we do our BFS from one, we want to calculate the distance to every single one of these vertices, which means to store that information, we're also going to need an int array, and I'll call it distances. And its size is going to be the size of our graph. The size of our graph is the size of the adjacency list. So we have our distances array over there. And by default, it's set to 0. So I actually could copy over all this code that I have over here and change one line, like add one extra line to do the task that I just described. But we're going to code it from scratch just so we get more practice. So the first thing that we're going to do is we're going to add 1 to our queue because that's the first vertex that we want to visit. And because we're visiting vertex 1, we're going to set it equal to true. And then we're going to keep on looping over this queue while we still have more vertices to visit, because the queue stores which vertices we have to visit. So we're going to keep on going over it while there's still more vertices to go to. Then we're going to get our current vertex. So I'll say int vertex equals queue dot pull. Then we're going to go through the neighbors. So for int neighbors, I'm going to use my adjacency list to get the neighbors of vertex. And then over here, I'm going to check if it's not visited. If the neighbor is not visited, it should be singular, by the way. Actually, it should be int neighbor, not neighbors. So if we have not visited the neighbor, then we want to visit it now. So we'll say visited neighbor equals true, because we want to visit the neighbor and we already have a bunch of stuff that's probably ahead of it. We have to add it to the queue. It cannot skip ahead of all the other stuff. It has to wait in line for its turn. So say queue.add neighbor. And this is where the modification comes in. So up until now, this has been exactly the same code that we had for our regular BFS. The modification is going to be that we have to calculate the distance to this vertex. And the distance, remember, because the BFS goes level by level, the distance to this neighbor, so distances of neighbor, is equal to distances of wherever it's coming from. So distances of vertex plus 1. And I hope this makes sense. So if we do a BFS from 1, and we add 3 and 2 to our queue. So now let's say we're visiting 3. The distance from 3 to 1 is going to be the distance from 1 to 1, which is 0, plus 1, because we just went one level further. Similarly, when we BFS from 3 to 5, the distance from 5 to 1 is going to be the distance from 3 to 1, because 3 is where we just came from. So this is going to be 1 plus 1, because that was an extra edge we just took between the two. So that's what this does over here. And then we can write a for loop. We can say, or actually, let's do this. We'll print out our vertex right underneath where we pull it. We'll say at vertex plus vertex, and then distances of vertex. So I'll run this and we'll see what happens. Okay, it ran the bipartite code. I'll run the BFS distance code. And yeah, let's take a look. At vertex 1, distance 0. Yeah, that makes sense. At vertex 3, distance 1. At vertex 2, distance 1. At vertex 5, distance 2. At vertex 4, distance 2. At vertex 7, distance 3. At vertex 6, distance 3. Yeah, that's correct. It worked. And this is and all we had to do was just change 2 lines of code, or rather we had to add 2 lines of code. We had to create our distances array, and then we just had to do this bit of code over here. So the point I wanted to make with this is once you know the steps for a BFS and a DFS, don't memorize the code, understand the steps and what the algorithm does, and then you can apply it to pretty much any situation, specific situations. So in this example, we just calculated distance between two vertices. And a practical example of this would be, that's a nice GIF. A practical example of this would be if you were representing a map as a graph, like pretend these were cities, and you want to calculate how many roads, the shortest number of roads you have to take to go from city 1 to city 4. Now you just wrote a program that can do that for you. And it works really fast, even if there are a lot of roads in a lot of cities. So I hope you guys found this example useful. And let me know if there are any questions about it. If there are no questions, we can take a 5-minute break. And when we come back, we'll discuss the priority queue data structure and discuss some more problems. Okay, it's 3 o'clock, so let's resume. We're going to continue by discussing priority queues, which are a type of data structure that are useful because of what they do. And we're going to be using them tomorrow when remember the shortest path problem I was describing earlier? We're going to be using them for that, solving that problem. One of the algorithms we'll be discussing, Dijkstra's algorithm, uses priority queues. So it's important to understand what they are. And the queue part may seem familiar to you. It does have many of the same functions that a queue has that we were discussing earlier, but it has this priority part. And this changes the function. The difference between a priority queue and a regular queue is that when elements are added, they are then sorted and stored based on their priority. And I didn't want to make some presentation about it because it's better to get some hands-on experience with coding it. So go ahead to REPL or whatever you use to code and create a new class. You don't need to copy anything over. We're just going to be working with what we have right now. And to create a priority queue, we would just say priority queue. And then inside the angle brackets, we provide a data type. So we'll start off by having a priority queue of integers. We'll call it PQ, and this is going to be a new priority queue. So this is how you create a priority queue. And let's go ahead and add some numbers to it. So I'll add 5, I'll add 3, I'll add 10, 1, and 2. Okay, so we have these 3 elements in our priority queue. And who remembers what that function was that we used to remove things from a queue back when we were doing our BFS?
Poll?
Oh, can you repeat that?
Is it poll?
Yeah, it is poll. So what we're going to do to print the elements in a priority queue, if you actually type in PQ and dot, if you're using something like IntelliJ, you can see all the functions that priority queue has to offer, which is why IntelliJ is pretty nice compared to REPL. And yeah, we have poll over here. I think if I hover on that, does it tell me what it does? Okay, it doesn't. That's fine. But my point is that unlike an array list or an array, we can't say like pq.get3. That doesn't work. And we can't say pq3. That doesn't work either. We can only access stuff from the front, really. So that's why we're going to write a for loop to go through the PQ while it's not empty. But actually, we'll write a while loop. While PQ is not empty, we'll print out pq.poll. Let's run this. And we added 5, then 3, then 10, then 1, then 2. But if you actually look at what it's printing out, it prints out 1 first, then 2, then 3, then 5, then 10. That's because by default, a priority queue will store the smaller numbers first. It'll store it in ascending order. With a queue, if this had been a queue instead of a priority queue, it would have printed 5, 3, 10, 1, 2 in the order we added those elements. But a priority queue is going to store it based on how small it's going to store it in the ascending order. And this is important for the shortest path problem because remember, the shortest path problem is figuring out which edges to take that lead to the smallest total total travel time. And therefore, you may want to consider taking edges that have a smaller weight than edges that have a bigger weight. And that's why we would use a priority queue and we'd create an edge object. And the priority queue would store edges based on their weights, their travel times. So that's what we're going to do right now. We're going to create an edge class and we're going to create a priority queue that's able to store these edges based on their weights, how long it takes to travel on those edges. So let's create an edge class. Let's go outside of your main function. And over here, you're going to type static class edge implements. Actually, we'll leave that part out for now. And somebody had typed in the chat all the way at the beginning. Amita had typed that, but she's not here now. But what are some properties that edges have that we may want to create in our class?
Weight.
Yep, they have a weight. What else do they have? Yep, they have vertices. Yeah, yep, they have 2 vertices that they connect to each other. So we'll have int weight and we'll have v1 and v2. we'll create our constructor for the edge class. We'll say int a, int b, int c, and then we'll just say v1 equals a, v2 equals a, and weight equals c. Okay, so we have our edge class in the constructor. And some of you said that you've taken APCSA. Do you remember that? Do you remember there's a particular function we can use to compare objects to each other? Does anybody remember what it is? I know it's been a while since the APCSA exam, but does anybody want to take a guess? There's a function that we can use to compare objects to each other. And there's an interface for that. There's a function we can use to compare objects to each other. This is a hint. This is the first 6 letters.
Is it compare to?
Yes, it is compare to. It compares the first 7 letters of the function name. Yep. So we can have our class implement an interface called comparable, and inside the angle brackets for comparable, we'll type in edge. Now, if you do Alt Enter on there, well, actually, if you're using REPL.A, that may not be an option, but it'll autocomplete. It'll just generate this compare to function for you. So this is the code that we just added. We're adding implements comparable of edge, and we have this compare to function. And what this function that will do is when we create our priority queue of edges, this function will determine what order the edges are stored in. So edges with a smaller weight, we want edges with a smaller weight to be stored at the front and bigger weight to be stored at the end. That's why over here, I'm going to replace return 0 with return weight minus o.weight. And what this does is if we return a negative number, it's going to place like this edge over here, this current edge object, in front of O. If we return a positive number, it's going to put O in front of this edge object, this current edge object. So this is our compare to function, and now we can go back to our main function, create another priority queue, and this time inside the angle brackets, we provide our edge class, and you can see that now it's showing up over here. I'll call it PQ, new priority queue, and I'll add some edges to my priority queue. So I'll say new edge, I'll add 1, 4, 5. The third number is the weight over here, so 1, 4, 5. I'll add 1, 2, 1, 2, 2. The vertice numbers don't really matter. I'm just putting in some random stuff. I'll have 10 for our weight. I will have, I'll have 9 for another, and then I'll have 3 here. Okay. And there's actually one more thing we should do before we start. Like if we take this code that we have over here, this while loop, and we just copy and paste it underneath and we run it, it's going to print out like some memory addresses of where the, it's going to print out some memory addresses for each of these edge objects. And this is another APCSA question. Does anybody remember what we can do to actually print out an edge object? If we want to format it nicely as a string, what can we add to our edge class to do that? We can add a toString method. So we can say public string toString. And remember, this function just returns a string that will be printed out whenever our object is tried. That'll be returned whenever our edge object is tried to be used as a string. So we'll return, in our toString method, we will return v1 plus 2 plus v2 plus just some formatting stuff. Weight plus weight. So print out vertex 1 to vertex 2 with weight, and it'll print out the actual weight. So now if we run this, you can see that our priority queue has stored these edges based on their distance from, based on their distances. Okay, I made a mistake over here. This should say v2 equals b. Now if we run this, that should fix it. Yeah. So we can see 1 to 2 with weight 2, 1 to 3 with weight 3, blah, 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 blah. The weights are the main thing I'm getting at. You can see here that it's sorted by weight. 2, 3, 5, 9, 10 in order of increasing weight. And yeah, just remember this and have just understand what it does for tomorrow, because we'll be pretty much using this exact same thing for tomorrow when we're discussing Dijkstra's algorithm. And I think tomorrow's meeting will be shorter than today's meeting because today we had to cover a lot of terminology and gain some more experience. So, are there any questions about the priority queue? Okay. Well, there are no questions about the priority queue. Um, Homework assignment. Code LinkedIn suggestions for you feature. So create a graph where the vertices represent people, and then from a given vertex, you have to print out that vertex's neighbors' neighbors. So if you have a LinkedIn account, or if you ever seen LinkedIn before, they have a suggestions for you feature where it gives you a list of people that they're like, hey, connect to this person because you may know them. And these people that they recommend are typically connections of your connections. So for example, you're connected to person B and D because you know people B and D. And the LinkedIn feature may say, why don't you connect to A and C? Because A is connected to B and you're connected to B. C is connected to B, you're connected to B. If D was connected to E and you were not, then it may also recommend that you connect to E because E is connected to D and D is connected to you. So basically, if you have anything if you have a neighbor in common with another vertex, the suggestions for you feature will display that. So that's one problem or assignment that you can work on to get a better to get a better understanding of these concepts and code that you just learned today. And the second more challenging one, slightly more challenging, is not too much more challenging, is implementing the Oracle of Bacon. How many of you actually checked out that website I sent out in the email? And then I also had on the slide over here. Does anybody check it out? No one did? Okay, we can check it out together. Okay, somebody did. That's nice. The Oracle of Bacon. Let's take a look at this. So if you haven't checked it out, basically Kevin Bacon's an actor. And what you can do is it allows you to search up like one person's name, one actor's name and another actor's name, and find a connection between them. So for example, we have Kevin Bacon and we'll do Charlie Cox. And if I type in find link, it's going to say Charlie Cox was in Stardust with Jason Fleming, who was in X-Men First Class with Kevin Bacon. So that's how Charlie Cox is connected to Kevin Bacon. He has a Bacon number 2 because he's 2 edges away from Kevin Bacon. And the reason I told you guys to check this out is because, I mean, by now you should probably have been able to figure out after today's lectures, this uses a graph. This website uses a graph to figure out how people are connected to each other. And I have some questions for you. What would a vertex represent in this graph?
I think it would either represent Kevin Bacon or Charlie Cox. Wouldn't it represent Kevin Bacon because we're trying to find a way to Kevin Bacon?
Yeah, the target vertex would be Kevin Bacon, but on a general, no, actually, the from vertex would be, yeah, it doesn't matter which order we go from, because I know they show arrows over here, but the edges are technically undirected. But yeah, Kevin Bacon could be represented to a vertex, but on a broader scale, on a higher level, what does a vertex represent? It represents an actor. So the vertices, the green boxes are the vertices, they represent the actors. And then I have a question for you. Then what are the edges in this example?
The
How,
movies that they star in?
yeah, that's correct. The edges would be the connections between the vertices, the connections between the actors, and the way that they're connected is the movies that they're in together. And remember how we discussed that there are weighted edges? If we were creating an edge class for If we're creating an edge class for Stardust, which is a pretty good movie if you haven't seen it, and X-Men First Class, which is another movie I love. If we're creating edge classes for these movies, or I mean, if we're creating edge classes to represent these movies, instead of having a weight like we coded over here, what do you think is another property that we could give an edge that would make sense? So if edges represent movies, what would be some properties of edges we would want to add to our class?
Like length, because it wouldn't be an integer then, it would be a string.
Yeah, we could add the length. We could also add the name of the movie. So
Oh, yeah.
yeah, so we could have like um, we would have our vertices as well as our actual the name of the edge. I mean the name of the movie, which would be another property. And one thing I wanted to add is when you're representing stuff like this as graphs, you may be wondering like, how do I represent this as an adjacency list? The answer is you have to map these. You have to map these strings into numbers, and then you build your adjacency list and do your BFS and all that sort of stuff with the numbers. And then when you're done doing that stuff, and you want to get the actual like name associated, you just go from the number to the string back to the string. So I don't know if that made sense, but basically you can't have like you can't have the indices in an array list be names or strings. Like you can have an array list. Yeah, array lists are indexed from zero and they go count upwards. They're numbers. You can't have like Charlie Cox as an index in an array list, but you can have Charlie Cox as a key in a map. We didn't cover maps in APCSA, but if that's something that you're interested in, you could take a look at them. They're not too difficult to understand. They basically have key and values that they use to store information. And the way that and they're applicable in graphs because then if somebody like if you're making a program where users can actually type in city names and how they're connected to each other, like city A is connected to city B, you could use a map to assign each of those strings a number, and then you use those numbers to make the adjacency list. You use those numbers to do the BFS and stuff. And then if you want to find, like for example, all the all the cities that city A is connected to, you have your adjacency list of numbers. Now you just use a map to go from the number back to the actual city string name. So yeah, that's why I wanted to show this example over here because it's pretty cool. And this is one of the homework assignments you can work on, implementing the Oracle of Bacon. You don't have to worry about representing vertices with strings, just focus on doing it with numbers. And the idea is you have to create a graph with numbered vertices. And given vertex 1 and vertex 2, you have to print all the vertices that you need to go from vertex 1 to vertex 2. So for example, from U to Al, you would have to print U, then Bob, then Al. Or from U to C, you would have to print U, then Doug, then C. So that's that homework assignment you can work on if you want. And then there's the LinkedIn suggestion for you feature. It's actually just, we have some time. I'm going to end early before 4:30. I specified 4:30 as the end time in case some days went on longer than I expected. So that's why I added that extra time at the end. Let's just, for the LinkedIn suggestion for you feature, all you have to do is really modify this BFS distance code over here. All you have to do is you have to just check over here if distances of neighbor equals 2, print out that neighbor. We can print out a suggestion for you, and then we could say neighbor. And we only care about going to vertices that are at most a distance of 2 from our starting point. So that's why after we reach a distance of 2, we're going to stop doing our BFS. Because if there's somebody In this network, let's say this like, A is connected to E and E is connected to F and F is connected to G. G is really far away from you. Like they're barely connected to you. Their connection is you. Yeah, and you don't want to have that show up in your suggestions for you feature. So that's why if the distances of neighbor, only while the distances of neighbor is um, less than 2, do we want to do our BFS and keep on doing it. So now if I just run this BFS distance code, that's pretty much the solution for this problem here. So suggestion for you is 5, suggestion for you is 4. Let's take a look at that. And yeah, you can see 5 is a connection to 3, 3 is a connection to 1, which is you. 4 is a connection to 2, which is a connection to 1, which is you. So that's the solution to that problem. Fairly simple. And for the for the Oracle of Bacon problem, um, let's just go ahead and code it today, because if we code it today, tomorrow's meeting will be shorter, so we can um, pack up earlier tomorrow. Okay, so let's go ahead and code this. We'll say Oracle of Bacon. And we will copy over our adjacency list function to save time. Okay. Actually, I'm not going to type this out either. I'm just going to copy and paste this as well. Okay. So for this, we're going to have to use something called backtracking. We're going to have to, so the logic, my logic for this, and there are multiple ways to solve programming problems in general, but the way that I'm going to tackle this problem, and you guys can also come up with your own solutions, is let's say I want to figure out the connection between you and Al. I'm going to do a BFS, and each time I go to a vertex, I'm going to keep track of where I came from. So for Bob, I'm going to keep track that I came from you. For Doug, I'm going to keep track that I came from you. When I do my BFS for Doug to C, I'm going to keep track that I came to C from Doug. When I do my BFS from Bob to Al, I'm going to keep track for Al that I got here from Bob. And wait a second, wait, the current vertex, or actually not yet, but eventually the current vertex I'm at will be Al. I'll eventually get to Al and I'll realize, wait, this is my target vertex. I don't need to do any more BFSs. So then I'll just break out of the while loop. And now I know who I used to come to Al from. I know that I used Bob to get to Al. So I'll go from Al to Bob. I know I used you to get to Bob, and then I come back to you, and we're at our starting point. So that's how we backtrack. Do you guys get that concept? The idea is we do our BFS until we get to our target vertex, and while we're doing our BFS, we keep track of the previous vertex we just came from. From Bob, we came from you. From Doug, we came from you. From C, we came from Doug. From Al, we came from Bob. And after our BFS, we just we would represent this as an array. We would use an array to keep track of who we came from, and then we just keep on going backwards in the array until we come to our starting position.